In the previous slides, we have talked about how to use hardware-supported atomic instructions to solve a critical section problem. However, this hardware-supported solution can be complicated and also in real world. So generally, it is inaccessible to application programmers, and it is very easy to understand because the operating system they won't allow the normal users to directly access those hardware instructions. So they belongs to privileged instruction that only can be done by kernel. So therefore, operating system designers they will build software tools to solve the critical section problem. The simplest one is Mutex lock. So here, the Mutex is shorted for the mutual exclusive. So actually, the Mutex lock is essentially a Boolean variable. So what the Mutex lock does is to protect a critical section where all the processes wants to access. So those processes they must call the acquire function to get the lock, then access their critical section. After one process exits the critical section, it has to call the release function to release the lock so that other processes can get the lock and access their critical section later. And the operating system will use the value of this Boolean variable to determine that so whether the lock is available or not. And also both the acquire function and the release function must be atomic in order to address the race condition problem. So usually they can be implemented through hardware atomic instructions. This slide shows us an example how to use a mutex lock to address the critical section problem. And also you can see that both acquire function and the release functions are implemented with several instructions. And those instructions must be executed as atomic instruction, which can be implemented by hardware atomic instructions. Then let's see a simple example. Assume we have two processes, P1 and P2. Both P1 and P2 want to access their critical section. So first, we put P1 onto the CPU. P1 will call the acquire function to get the lock. Since no process is using the lock, the value of available is true. So after we add the exclamation to available, the whole thing will become to false. Therefore, P1 won't stuck at the while loop, then set the value of available to false. Then P1 can access the critical section. So in worst case, P1 has been interrupted by P2 and taken off the CPU. Then P2 has been put on the CPU. Then P2 will call acquire function to get the lock. So currently, the value of available is false. The condition within the while loop will be true. So P2 will be stuck on the while loop until P1 release the lock. So after a while, P2 is interrupted by P1. Then P1 continues its progress and exit the critical section. Then P1 calls release function and change available to true. Then keep executing the remainder section. Then P1 is interrupted by P2. So since available is true now, P2 will out of the while loop and change available to false. Then P2 access the critical section. So from this example, you can see that. So how can we use acquire function and the release function to protect the critical section? However, from this example, you may see that. So while P2 is waiting for the lock as stuck in the while loop, P2 actually keeps looping in the while loop. So we call this phenomenon as a busy waiting. So therefore, the lock is called spin lock. So for using mutex lock solution, there's a trade-off there. So since P2 is stuck in the while loop, as long as P1 release the lock, P2 can immediately grab the lock and do the progress. So that is the advantage of using mutex lock. But on the other hand, since P2 is stuck in the empty while loop, it will continuously execute inside the CPU and waste the CPU resources because P2 did not do any meaningful progress. It is just busy waiting there. So before you want to use a mutex lock, you need to think about this trade-off carefully. If the expected waiting time is short, so using mutex lock can reduce the waiting time when the lock is available. However, if the waiting time is too long, so using mutex lock will waste too much CPU resources due to the busy waiting or spin lock.